So you're kind of brute plugging it in, right? So when you plug in 3 pi over 2 or negative pi over 2, you're going to get 0. So like this is your starting point, right? Like you're starting right here when you start using that symmetry, right? So then as you do 5 pi over 3, you're going out just a little bit. As you go towards 0, you're going out a little bit further. Sorry, this is like not as pretty as I'd like, but that's fine. So you're going out a little bit further, so you get a little bit of like a curve here, right? And then it gets further and further out, and its max goes up to pi over 2. Which makes sense because that's when sine equals 1, that's where you're going to get your biggest radius. Okay, so then using your symmetry, right, like if I'm going to find the area under this thing, which we'll do tomorrow, you're going to be integrating from negative pi over 2 to pi over 2, but then doubling it. So the multiple choice on the polar is very difficult because you'll do it like the way you like it, which is like usually the easier way, which that's what I do too. But then they're going to make you adjust it based on symmetry or like on how they want it, apparently. So basically for corduroys, that's what this one is you're going to use that symmetry to your advantage. So then now you can, oops, oh boy, oh no, whatever. Oh, that's okay, maybe. Something like that, okay? You'd use your symmetry to get the rest of it, okay? Which makes sense for sound. Because, like, obviously your sound direction is going forward, but you still will get some sound behind the stage, like behind where you are standing. All right. So things from earlier, okay? So things with patterns with this, okay? So maybe I'll just rewrite this over here. 3.5 plus 3.5 sine theta, okay? The graphs with the roses have a number in front of theta. Remember, it's odd or even. That depends on how many roses there are, okay? Now, these guys are your cardioids. So sometimes, depending if one's bigger than the others, there's going to be like loops and things like that. So for this, what I like to do if I'm just totally ballparking it is I'll like to figure out like maybe when does this equal 0? You know, 3.5 plus 3.5 sine theta, right? So you can try to, you know, if you solve that, you get -1 is your sine theta, and then you can figure out when does that happen? When does sine equal -1? So, right, that'd be negative, wait, what am I doing? No, it's not there. Right, so if sine equals -1, we look at the graph, that's going to be 3 pi over 2, which sure enough, that's when our radius equals 0. Right, so instead of making the table, you can try to figure out like, okay, that's when my graph is going to come back to 0. Okay, other things that I like to do is figure out like when's my biggest radius going to happen. So like if you're looking at this equation here, you know your biggest radius is when your sine equals 1, right? So when my sine theta equals 1, right, that's going to be when my radius is the largest, right? So looking at that, that's going to be at pi over 2. So you can start, if you know what the graph is roughly going to be, you can try to figure out like, okay, where am I back at my origin by figuring out when does my r equal 0, and then figuring out where is my r at my largest point, like furthest out. When my radius is 7 is when the sine equals 1. So you kind of have to manipulate the equation just so you can get a vibe for what it looks like. They're not going to make you like plot individual points, really, like what we did here. You're just going to have to know like what the graph roughly looks like. So moving on to like something like this guy. So when you're looking at this equation, you should say rows. Okay, like you should look at that and know it's rows. I do have in this packet and on your like little mini packet, these are all the different ones. So you can kind of have all of that here. You might want to add, what else did I have? If you have R equaling like a number, that's just your straight up circle, right? That's like your normal circle. What else is there? If you have R equaling theta, okay, that's your spiral, Archimedes spiral. What else is there? Oh, theta equaling a number. Where do I write that? I'll do it over here. So theta, or not theta, sorry. Yeah, theta equaling a number. That's going to be your line. Okay. So those ones are kind of like the ones we did on those other days. But I think you already know the radius equals like 5. Okay, that's just a normal circle, radius 5. Okay, R equals theta, like as your angle increases, your radius increases. So as you turn, you get further and further away from the origin. So that's why it creates a spiral. This one, if theta equals a number, you're literally just turning, and then your radius is like free for all. So it's like you could have positive radius, negative radius. They didn't put any bounds on the radius. So you're just kind of going out forever and then back the other way forever if the radius was negative. So we've done that before, but maybe just having it all in one spot, okay? What else can we say? We're going to talk about lemon skates in a little bit, but here we're on the rose curves, okay? So remember, like sine is symmetric with your, like the y-axis, quote unquote, and then cosine is with like, quote unquote, the x-axis, the polar curve. If they're even, it's double petals. Odd is the exact amount. A lot of things is trying to figure out when do you get a full petal or when do you get at least half a petal to figure that out. So going back to here, okay, if we're just like straight up graphing this thing, okay, what I'm paying attention to is I want to figure out when is it to the center and when is it going to go and go out for one full petal? Yeah.
So when you first looked at the equation, like what was the first thing that made you realize that there were rows?
The first thing was there was a 3 in front of the theta because all the roses have like numbers in front of the theta. And it had an amplitude. It's in this form. So like all rose curves are in this form. And all cardioids have, or limicons, I guess I keep saying cardioids, but they're technically called limicons if you talk about all of them. But this one has like addition and subtraction with it, but there's no scalar on your theta. So it just kind of depends on like where your numbers are, pretty much. And then circles, there's no scalar on the theta, it just has amplitude. And then lemon skates we're going to talk about in a little bit. All right, so for this one, you're like, okay, rows. So the first thing I like to do is I'm going to figure out, like, when is it at its center? So first, looking at this, you're going to say rows. Things you can also notice is you can be like, oh, there's going to be 3 petals. So maybe I'll start with that before we get into the nitty of the graphing. Okay, there's 3 petals. This guy we have as, this is how far it's going to go out. That's like your amplitude, or like the furthest it's going to go out is 6. Your biggest radius is going to be 6. You can look at that it's sine. So your symmetry is going to be like the, I mean, technically you're supposed to be, say, theta is pi over 2, but like the y-axis for sine. Okay, so you're kind of having that idea, so that's going to be like negative pi over 2 to pi over 2 is like where you're going to get your symmetry on this thing. Okay, so looking at just the equation, I can get a little bit for it, but now what I'm going to do is figure out like what is my, maybe I'll start with red for the rainbow. You're going to figure out when it comes back to the center. When is it at its center? Okay, so when is it at its center? That's when your radius equals 0. Right, so 0 equals 6 sine 3 theta. Okay, so the amplitude's kind of useless, just divide it out. And then when you're dealing with a scalar on your theta, essentially what you do is you figure out, like, when does, like, think, like, when does your just sine of x equal 0? Right? So, because, like, once you have that angle, you can use the 3 and deal with the 3 in a little bit. So if we set that equal, when does sine equal 0? That happens at 0 and pi, right? But because we're dealing with the scalar, okay, what you're going to do is you're going to say when this whole angle here equals 0, that's my angle, right? Or when does this whole thing equal pi? So the way you solve that, like algebraically, is you take this 0 equals 3 theta, and then you take your pi equals 3 theta. So you're going to be back at 0 at when theta equals 0 and at pi over 3. Okay. So I'm going to complete one petal between 0 and pi over 3. Right? Because that's when it's going to come back to 0. So what I kind of like to do is, so like here's 0, here's pi over 3. I'm going to get a full petal in there. Okay? Now, because the petals are symmetric themselves, okay, I can cheat a little by knowing, like, when is it going the furthest out. So my second step, what I do is figuring out, like, the largest R. Right? So for this one, I know it's going to be 6 because that's the amplitude. But when that angle happens, it's going to be midway between the 0 and the 3 pi. So the largest R, I already know is going to be 6 because this is the amplitude, right? This is the amp from the, like, the equation. And then for the angle itself, because the petals are symmetric, it's going to be a pi over 6. Because that's halfway between the 0 and the pi over 3. So this is going to be at pi over 6. So you don't really have to do much math. Another way you could figure that out, say like you can't do fractions today, you could just figure out when does the sine equal 1. Right? So like you could just figure out like when does the sine of 3 theta equal 1. And you're going to say pi over 6. So it kind of depends. So then here from 0 to pi over 6, you're going to go out to 6. So that's going to be their furthest value to get there. And then if you want to get some more points, I mean, pick some values in between. So like for 3, get a few points by plugging in, like, I'm going to go the farthest is pi over 6. Well, now I'm going to try, maybe I'll plug in pi over 12. Right? So to figure out your R, you do 6 sine of 3 and then plug in pi over 12. Right? So what would that be? 3 root 2? Right? Yeah. Yeah. I'm like second guessing myself. So, I mean, that one is going to be, what is 3 root 2? That's like a little past 4, isn't it? I think so, yeah. A little bit past 4. And because it's symmetric, you can use that over here. And then here you have is a rose curve. At least one of your rose curves. Okay. You can use some symmetry here if you want. Okay, so here we're going to have some symmetry here. So you know that this other petal, right, is going to be coming at over here as well, like basically on the left side of that graph. Okay, so pi over 6, if I do the reflection, that's going to be 5 pi over 6, right? And we're going to be here, and then we can get your, you're a little bit past 4s over here, and now you have your other petal. Okay. And then you're thinking, well, there's supposed to be 3 petals, right? So again, this is all like strategy of getting like what the curve looks like. You can always just throw in numbers, but if you don't have a calculator, you're kind of like, what am I supposed to do here, right? But you're supposed to have another petal if it's going to be reflected with this pi over 2, right? And we're doing 3 of them. You could also plug in like maybe another step is you could plug in, shoot, I'm running out of colors here. Maybe I'll do 4, I'm going to do 6 sine 3 and plug in 3 pi over 2 to figure out what's going on with those graphs. So that could also be part of part 3. So 9 pi over 2, you're going to have to do some coterminal angles here, or you could plug in pi over 2 and use the reflection. But here we go, that's going to be out to 6, and then here's your last petal. Okay. So there's different ways. I mean, that's how I work with the rose curve. Figure out where you get 1 petal. Usually with area, you really only need 1. If you know there's 3 of them, really what I could do is just find the area of 1 and then multiply by 3, right? So if you can get at least just 1 petal, you're going to be good. Because then you can use the equation to figure out like how many petals there are and figure out the area that way. Is there any questions on how it works? Okay. This is the last one. This one's the easiest one, honestly. These are called the lemon skates. Okay. This doesn't work with symmetry like that rule. It's because of the r squared messes everything up. Okay. Now, it only looks 2 different ways. So if you look at these graphs here, those are the only options. Okay? So for sine, it always is like this diagonal thing going on. Okay? If it's cosine, it's always like looks like an infinity sign every time. So really what you just need to do, because again, you're just going to be finding areas of these. You're always going to get 1 loop between 0 and pi over 2 for sine. This one, you'll get half of 1 between 0 and pi over 2. Or you could get a full one from negative pi over 2 to pi over 2. You can get a loop. So really, you're just figuring out how far the loop's going to go out, essentially. And that's your A. So this is usually a perfect square because they're not that mean. So like you just square root it and that's how far you're going to go out. So if it's sine, you're going to go out at pi over 4. And then if it's cosine, you're going to go right on the polar axis. So if you're looking at this one, I'll show a cosine one too really quick. But like basically what I do is I figure out, okay, here's 16, right? So what I'm going to do is figure out, okay, if 16 is that a squared value, my a is going to be 4. I just square root it. Okay, so then what you're going to do is, because your sine function is symmetric with the pole, the 2 little loops you're going to get is going to be radius of 4, and you're going to turn pi over 4. So one of them is going to be out to 4 at pi over 4. And then the other one is going to be at negative 4 pi over 4. And that's because it's sine. So this one is going to be the other one. And this is how you're gonna, oh boy, that looks bad too. How you're gonna loop it. Oh boy. Well, this doesn't look as nice, but that's how it would be. Yeah.
How did you get, like, how did you know it was pi over 4?
Because it always goes out to pi over 4. This is always pi over 4.
Like,
Every single one. Yep. 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 So then if it was, I don't have an example of cosine, so say it was r squared equals 16 cosine 2 theta. That graph would just be out to 4. And it would be like a infinity symbol. All right. So this one doesn't have many options to be varied. The roses are annoying, but as long as you kind of can get a feel for what that's looking like, you can get